Sir, good morning, sir.
Good morning, Samuel. How are you?
Yeah, I'm fine, sir.
Right. So nice to see you. Slide 2 minutes, we will take out the time. So
Sure.
just now the tracks are going to be completed. So in
Okay.
few minutes they will be joining.
Okay, sir.
Right. Just 5 minutes it will take. And you can take up your own time and you can continue it.
Yes, sir.
Right.
Okay.
It's not to be completed before 30 minutes also.
Okay.
So 5 minutes we will wait for them, participants
Sure.
to join over there. And then
Yes,
we
sir.
will carry on.
Yeah. Okay, sir. Thank you.
Yeah. Thank
Uh,
you.
Sir, sorry for the delay. Good morning, everyone present here. I, Aditi Karsolia, on behalf of our ECE department, would like to welcome our next keynote speaker, who is Engineer Samuel Jigney Harrison, sir. He started his engineering education from St. Joseph's College of Engineering, Chennai, with a bachelor's degree in the field of electronics and communication between 2004 and 2008. He then completed his master's in science, specializing on integrated circuit design, a joint degree from Nanyang Technological University, Singapore, and Technical University of Munich, Germany, in 2010. He also holds a master's in business administration from Anglia Ruskin University, UK. During his studies in these three institutions, he published journals and papers in different conferences and national level symposiums. Sir started his career with Avago Technologies, Singapore in 2010 as an entry level IC design engineer. He then got pronounced as the senior ASIC design engineer in 2014, and the company was renamed as Broadcom Limited Singapore in 2016. He is currently working with ST Microelectronics Asia Pacific Private Limited, Singapore, since 2017 as the Senior Digital IC Design Engineer. He has 11 years of experience in VLSI, specializing in physical design implementation with 90, 65, 40, 16, and 7 nanometer technologies, covering areas like floor planning, place and route, clock tree synthesis, static timing analysis, and physical verification. He has also received the Technical Merit Award in SNUG Penang 2018, conducted by Synopsys, for presenting a paper titled A Novel Approval in Security Implementation and Clock Tree Synthesis Using ICC2. He has also published an article titled Importance of Security in IC Design by the Singapore Semiconductor Industry Association in their technical magazine Singapore Semiconductor Voice in May 2019. He is also the fellow member in Indian Society for Very Large Scale Integration Education, Ranchi. He also has the membership for certain technical societies like VLSI Society of India, Semiconductor Society of India, the Institute of Electronics, Information and Communication Engineers Japan, Engineering New Zealand, IEANG, Society of Electrical Engineering Hong Kong. Sir is also an associate at the Institution of Engineers of Singapore, Singapore Semiconductor Industry Association. He is also the member of the Institution of Engineering and Technology, UK. He is the senior member at International Economics Development Research Center, Hong Kong. Now, I take the privilege to invite him on speaker panel. Welcome, sir.
Thank you, ma'am, for the brief introduction. And once again, I warmly welcome all the participants of the conference, and it's a great privilege to be a keynote speaker in this first international conference on recent trends in parallel and distributed processing techniques. So now moving on to the presentation. I work with ST Microelectronics, which is Europe's largest semiconductor chip maker and one of the world's largest semiconductor companies with its corporate headquarters at Geneva. We serve around 100K customers around the globe with 11 manufacturing sites, and we have around 46,000 employees worldwide with 18,000 active patents. So Singapore is the headquarters for the Asia Pacific region and has both back-end and front-end facilities. So in ST, we build products that enable smart mobility, more efficient power and energy management ICs, and widely deployed IoT and 5G technologies. The four end markets of ST Microelectronics are automotives, industries, personal electronics like the gadgets we use, the smart watches, etc., and communication equipments. Okay, so today's keynote lecture is into physical design. So what is physical design? The circuit representations are converted to geometric descriptions. So in the IC design flow, we have both front-end and back-end design. So the output from the front-end design team is given to the physical design team. So all the circuits are being converted to geometric shapes. But the functionality will still remain the same. It is only a conversion of the circuit to metal layers. So in this image below, you will see the front-end team who does the RTL design, functional verification, and then the back-end team who does the physical design and design integrity checks. And from the physical design team, the GDS output is given to the fabrication plant. Okay, what are the significant aspects of physical design? The role of physical design significantly increased in the 90s, and the two main reasons for this dominant increase are the deep submicron scaling and the interconnect optimization. Okay, so what are the challenges in ASIC design? The cost, resources, trainings, tools, competition between design houses, and the tight deadlines and in the project cycle. All these are very high challenges in ASIC design and the complexity in the design because of the shrinking technology. What are the steps in physical design? The main steps in physical design are floor planning, power planning, placement, clock tree synthesis, routing, static timing analysis, and physical verification. Okay, so what are the risks involved in physical design? Failure in any one of the steps in physical design will lead to chip failure, and respin of the chip is quite expensive, and this may even result in closure of business deals. So this is a very critical task employed in the IC design flow, and incomplete development of EDA tools also is a risk for physical design, and lack of experienced resources. Okay, so the first step is floor planning. A well-planned floor plan helps to improve congestion, timing skew, and DRC violations. So here you see macro placement in this figure given below, where a group of macros which communicate with each other are clubbed together in different colors so that there is less congestion and it is easy to close timing. And since all the macros are at the boundary, you have plenty of space in the middle so that the standard cells can be placed properly. So how can we achieve a good floor plan? Macro placement to get better timing and minimum skew. Macros and standard cells should be placed on grid, and balancing skew is very important in physical design. Hence, the clock cells can also be placed in floor plan itself, and tools can balance the skew. The next step is power planning. Power planning should be done with utmost care so that the cells that design get proper power. So it is a very important step where we need to make sure that all the components in the floor plan are getting powered up. So all the VDD and ground pins are properly connected to the VDD and ground power stripes. So the power stripes structure should be correct, and the pattern is VDD, VSS, VDD. And power straps of the IPs, memories should be properly aligned and connected to the parent power module. So power pads should be properly placed, and we need to make sure that there is no hotspot during power planning. Here is a pictorial representation of a power plant where you have a VDD VSS core ring at the boundary, and then you have power pads on both the sides. So one is a VDD and pad, and one is a ground pad, and you have trunks which run horizontally and stripes which run vertically, and you will see that all the standard cells are properly connected by VDD and ground power stripes. So basically the whole structure is properly powered up. The second step is placement, where placement of standard cells takes place. The place and route tools have good ability to do proper placement of cells. So placement tools are Innovus from Cadence and ICC2 from Synopsys. Majority of the companies, they prefer to use Cadence for place and route. So this tool has the ability to do proper placement of cells, provided we have a good floor plan as an input. So proper placement helps to improve the burst negative slack, total negative slack in terms of timing and also congestion. And placement is congestion and timing driven in Innovus. Spot is in red. So we need to make sure that we fix this congestion so that we have then in CTS step it will be more helpful in timing closure. So what is the idea behind clock tree?